Hello everyone. Thank you for coming. My name is Jiyue Jiang. Other is Dongchen He. And today I will be presenting Keyforge, attributable email from forward forgeable signatures. This approach is meant to be a new form of email authentication, similar to DKIM. I am excited to share how this solution can keep emails in real time, but not let all the messages be used as proof forever. First, let's acknowledge the critical role of email. It's key communication channel for personal, uh, uh, organizational, and governmental needs. Spam and siphon are major issues, and DKIM or domain case identified mail was designed to combat this by having the sender's mail server sign outgoing emails. On the receiver side, these signatures are verified by looking up a corresponding public key. The drawback is that once DKIM signatures are leaked, um, possibly through a mailbox, they can serve as undeniable evidence that an email is legitimate. That can end up hurting privacy if emails are shared for published later. Okay, let's move on to the motivation for non-attributable email. Actually, a lot of email leaks happen all the time. Uh, Breaches like YAF or the DNC hacks are good examples. With standard DKIM, if someone steals your signed emails, they have strong proof of authenticity. This data can be used for blackmail or serve reputational damage because no one can easily deny the validity of those signatures. This goal is to maintain effective spam or and subfin defenses, but make it impossible for attackers to prove the authenticity of stolen emails to the outside world once they have been compromised. Okay, why is this a hard problem? These authors use a store and forward model, which means emails pass through multiple servers, including possible forwarding and mailing lists. You cannot always identify the final recipients beforehand. Long-lived keys are the normal for DKIM, so the authors rarely rotate things that can be risky. Emails are sent in the huge numbers, so any new solution must handle large throughputs without performance bottlenecks. And we cannot break existing email follows. Any new system must work smoothly alongside current standards. Okay, we can consider two main threat models. The first one is after the fact attacks. The attacker screens a snapshot of your stored emails. For example, by hacking into your mailbox. They want to use the stolen emails to prove authenticity to third parties. The third one is that real-time attacks. The attacker monitors your inbox as new message arrive. Their goal is to leak incoming emails right away and prove they are legitimate. The authors boil down the requirements into five key points. The first one is the first one is that they still need to confirm the emails come from a real domain. Second, stolen emails shouldn't be uh, provenable. The third one is that the sender cannot require extra handshakes. The sender often doesn't know the final recipient. The fourth one is that they want to avoid a consistently rotating case. Finally, any new solution should fit well in the existing email ecosystem without too much disruption. In this figure, we can see how email typically travels in the store and a forward architecture. Multiple mail transfer agents, that is MTAS, might forward your message. Verification of authenticity often happens at the receiver's mail delivery agent, that is MDA. The figure illustrations show how an email starts at the sender's email client, moves through outbound MTAS, and finally arrives at the reception's mailbox. Okay, let's move to the forward forgettable signatures, that is FFS. Why? FFS introduced a concept where signatures are valid for a certain period. Once that period expires, the signatures can be forged by anyone, can thus no longer offers a stronger proof of authenticity. The idea is unforgeability during the fresh period. It's a Barry mechanism that makes all the signatures publicly forgettable after some delay. This way, recently delivered emails can still be authenticity to prevent spam, while old emails cannot be used as proof in a damaging link. Keyforge solves this problem with a brief FFS-based scheme linked to timestamps. Each email is signed with a time tag predicting arrival time plus a margin triangle. After triangle time, the server publishes its binary data so that older signatures become forgettable. This means email older than triangle cannot be proven authenticity. Real-time attacks still exist, but cannot keep a preeminent proof of authenticity. Keyforge uses hierarchical identity-based signatures. Time is split into year to month to day to 50 mini chunks. After each 15-minute chunk, the domain publishes key data for that slot, making all the signatures forgeable. This layered approach uses the minimal key information periodically, saving bunch wise. Like DKIM, no extra communication is needed between sender and receiver. Only free a few kilobytes of data per month. Published via DNS or a web server. Signing can be faster than RSA. Verification is slightly slower, but usually not a bottleneck. Can reduce bandwidth usage. TimeForge is an external service that confirms the current time. A statement like current time is 13. We can see this. A statement like current time is larger than t can replace consistent key publishing. If we can show 10 plus t plus larger than t plus triangle or older signatures become forgeable. Great for setups where continuous key release is not ideal. Let's move to the benefits and the limitations. About benefits, there's no need for regular key uh, revealing by the sender. The second is the tape is time-based forging can be simpler in some distributed system. About limitations, the first one is relies on external time authority. If compressed forging could happen to earlier, might need complex zero knowledge proofs, adding extra overhead. About uh, about a photo type built for postfix, a common mail server. About 2,000 lines of code in Go, C, and Python language. A small mail filter handles sign and verification. A key server manages the secret keys and publishes its binary information. Minimal changes to normal mail flow. Just add or verify a special header like DKIM. Okay. It's better information published via DNS or a small web server. Okay. Okay, let's move on to the performance result. This is example tables. Keyforge often shows faster sign-in compared to RSA 2048. Verification might be a bit slower, but not severely. Signature size vary, sometimes slower, sometimes a bit larger. Okay. Time forger is heavier, but offers stronger time-based deniability. Okay, we can see this. Okay, we can see this table. It's show performance comparison. Okay. Uh, with uh with a big chunk. Uh, its binary data can be free megabits per month. Okay. It's per month. Splitting by year to month to day to chunk, reduce it to a few kilobytes monthly. This makes the large-scale adaptation easier. Use the DNS or a lightweight web server. Okay, and we can see this result is bare information overhead. Okay, it's bare information is equal to k published each time period. Example is every 15 minutes. Okay, compressed hierarchical else field KB per domain per month. This table is representative overhead for K-Forge Xperia data. Okay, let's move on to the conclusion. K-Forge and Time-Forge improve on DKIM by allowing all the emails to be non-attributable. And FF-based delayed or time-based expire ensures no attributable post triangle. Okay. Second, delayed or time-based expiry ensures older emails cannot be proven authenticity. And we can see enhanced solution that target real-time attackers via forge requires peer reception domain signatures. Okay. About the performance, this performance and the development is critical compared to RSA-based DKIM with minor overhead in some aspects. Okay, extended models handle real-time components by adding more foreign on requires the features. Finally, takeaway. This is a variable path for non-attributable email at internal scale. This performance is overall pretty close to RSA-based DKM. Okay, let's move to the feature directions. Working with the IETF to standardize these ideas for email security. Okay, encouraging adoption within the IDTF, incorporating into new DKIM updates. Possibly specific time forge with multiple independent PVTK providers. Okay. Add advanced security for malicious MTAS and complies the mailing list. We can keep it user friendly. Its domain administration easily grasp forging, and end users see no big changes. Okay. Transport to end users to ideal and clear communications for mail forging concept to domain administrations. Okay. Next, Dongchen will share the next paper.
Oh, okay, let me share my screen. So just wait a minute. Oh, okay, hello everyone. My name is Dongchen, and I'm honored to present the work titled HeadStart, efficiently verifiable in the low latency participatory randomness generation at scale. And this research is a collaboration work between the National Taiwan University and UIUC. Today I will walk you through the motivation, design, and the evaluation of HeadStart. And this is a protocol that addresses critical challenges in randomness generation for public participation. Let's begin. So firstly, I will give you a brief introduction. As we all know, randomness is a fundamental building block in many applications that serve the public interest. For instance, consider vaccine allocation during a pandemic. Randomness ensures fairness in selecting individuals for limited vaccine doses. Similarly, randomness is used in price-linked savings accounts to reward savers and in lotteries to ensure fairness. However, existing methods for generating randomness have significant limitations. Many rely on centralized systems, which lack verifiable proof of unpredictability and bias resistance. This undermines public trust. Our work addresses this gap by introducing HeadStart, a participatory randomness protocol designed to be scalable, efficient, and also verifiable. And for this slide, let's delve deeper into the motivation behind this work. Public confidence in randomness has been eroded by incidents of tampering and manipulation. For example, there have been cases where lottery results were rigged or where randomness used in public resource allocation was questioned due to a lack of transparency. Participatory randomness generation offers a promising solution. It allows individuals to directly contribute randomness and verify the process. However, existing protocols still face two major challenges. The first one is scalability. How do we handle millions of contributors efficiently? The second one is usability. How do we ensure that contributors with limited computational resources, like mobile phones, can participate? These challenges motivated us to design HeadStart, a protocol that addresses these issues while maintaining strong security guarantees. And for this slide, we will introduce the key challenges. To summarize, there are four key challenges in designing a participatory randomness protocol. As you can see, the first is unpredictability. The result must remain unpredictable until the contribution phase ends. And for the second part, it is bias resistance. Adversaries should not be able to manipulate the result to their advantage. And for the third one, it is scalability. The protocol must support millions of contributors without significant overhead. And for the fourth one, it is usability. Contributors should be able to participate using commodity devices like smartphones or your own laptops. These challenges are non-trivial, especially when we aim to achieve all four simultaneously. Existing protocols often excel in one area, but fall short in others. And HeadStart is designed to overcome these limitations. And for this slide, let's look at the HeadStart protocol. The key innovation of HeadStart is dividing the contribution phase into multiple stages, denoted as L. This allows us to give the result generation phase a head start, significantly reducing the result publication latency or RP latency. The protocol uses two key cryptographic tools, Merkle trees, to efficiently store and verify contributions. And the second one is verifiable delay functions. We can also call it VDFs, to ensure unpredictability and bias resistance. Together, These tools enable HeadStart to achieve scalability, usability, and security. Let's break this down further. So for this slide, we'll introduce the key features of HeadStart. As you can see, HeadStart has three standout features. The first one is about scalability. The communication and verification complexity for each contributor is all log C, where C is the number of contributions. And this will ensure that the protocol can handle millions of contributors efficiently. And for the second one, it is usability. Contributors can participate using commodity devices with minimal computational burden. For example, even a 7-year-old smartphone can handle the verification process in seconds. So we can see this is the meaning of usability. And for the third one, it is low RP latency. By dividing the contribution phase into L stages, the latency is reduced to T divided by L, where T is the total duration of the contribution phase. And this is a significant improvement over existing protocols, which often require T additional time for result publication. Okay, so for this slide, we will introduce the contribution phase. Here's how the contribution phase works in HeadStart. The phase is divided into L stages, and each stage allows contributors to submit random values. For example, if L is equal to 100, the contribution phase is divided into like 100 smaller time intervals, right? And at the end of each stage, the organizer computes a Merkle tree root, which serves as the commitment to the contributions in that stage. And the result generation phase starts L-1 stages earlier, allowing the final result to be published shortly after the contribution phase ends. And this approach just ensures that contributors have enough time to participate while minimizing delays in publishing the result. For the details, we can refer to this diagram on this slide for a visual representation. And for the next slide, we will introduce Merkle trees. Merkle trees play a crucial role in HeadStart. They're efficient data structures that allow proof of inclusion with all log C complexity. And here's how they work. Firstly, each leaf node represents a contributor's random value. And then, long leaf nodes are computed by hashing their child nodes. And for the last, the root node is published as a commitment to all contributions. As we can see, contributors can verify that their input is included by checking the audit path, which is a sequence of hashes leading from their leaf node to the root. And this ensures transparency and verifiability. So we can also see that the details of these Merkle trees from these applications and also from the verification complexity. And for the next slide, we'll introduce verifiable delay functions, VDFs. As we can see, a VDF or verifiable delay function is another key component. It is a cryptographic function that requires sequential computation, ensuring that the result cannot be computed faster than a certain time limit. The VDF in HeadStart has three components. The first one is setup. We will initialize the VDF with a security parameter and time parameter. And the second one is about evaluation. We should compute the result using sequential operations. And the third one is about verification. We can quickly verify the result using a proof. As you can see, the beauty of VDFs is that they ensure unpredictability and bias resistance while being efficient to verify. And for the next, HeadStart also satisfies three critical security properties. The first one is unpredictability. So what is unpredictability? As we can see, adversaries cannot predict the result before the contribution phase ends, even if they know all current contributions. And for the second, bias resistance. Adversaries cannot manipulate the result meaningfully, even if they control a subset of contributors. And for the third one, verifiability. Contributors can independently verify the correctness of the result using Merkle-tree audit paths and VDF proofs. And all these properties make HeadStart robust against both passive and active adversaries. And for this slide, we will show you some algorithm improvements. To further enhance performance, the authors just introduced two algorithm improvements. The first one is hash. So an efficient hashing algorithm that maps strings to class groups of imaginary quadratic fields, and this enables proof aggregation for VDFs, reducing the proof size and also verification overhead. And the second is about DHPI. It just determines hash prime iteration, which speeds up VDF verification by skipping field primality tests, and this optimization just reduces verification time by up to 5 times. And let's get a more detailed detailed description about the hash. As we can see, hash is a novel algorithm that solves a key problem in VDF implementation, efficiently mapping strings to class groups. By enabling proof aggregation, hash reduces the size of VDF proofs and the computational burden on contributors. We can just refer to this diagram of hash workflow to get a detailed description about how this algorithm just work. And for the next slide, we will introduce DHPI. As we introduced before, DHPI optimizes the verification process by skipping field primality tests. The organizer provides the iteration count for valid discriminants, allowing contributors to verify the result more quickly. And this is particularly useful for contributors with limited computational resources, such as mobile phones or just some old laptops. After that, we will introduce the evaluation metrics. So about evaluation metrics, let's now discuss how we evaluated the HeadStart. We just focused on three key metrics, as you can see from this slide. The first metric is scalability. So scalability means that how well the protocol handles a large number of contributors. And for the second one, it is verification efficiency. This means how quickly contributors can verify the result on commodity devices like smartphones or laptop. And for the last one, it is RP latency. It means how quickly the result can be published after the contribution phase ends. So after that, we can see the scalability. So HeadStart is highly scalable. The communication complexity for the organizer is OC multiplied log C, while for each contributor it is O log C. Verification complexity, as you can see, it is L times just polylog T plus log C. So this ensures that the protocol remains efficient even for millions of contributors. We can have a very detailed understanding of this by looking at this diagram or this graph of verification time versus the number of contributions. And for the next, we will introduce verification efficiency. Verification is highly efficient on commodity devices. For example, on iPhone XR, it takes just 6.21 seconds to verify the result when L is equal to 1. Proof aggregation further reduces the verification overhead, making HeadStart practical for everyday users. So this is how verification efficiency means for this work. And for the next slide, we introduce RP latency. So for RP latency, it is like result publication latency. HeadStart significantly reduces RP latency by dividing the contribution phase into L stages. The latency is reduced to T divided by L. For example, setting L is equal to 100 reduces the latency by 100 times, allowing contributors to receive results much faster without compromising security. And this is how HeadStart just improves the RP latency and also the result. Then we will introduce a use case. One practical use case for HeadStart is equitable vaccine allocation. Such events requires a long contribution fees for public registration and fast result publication to avoid delays in vaccination. HeadStart enables fair and timely allocation by reducing RP latency. Okay, so then we will introduce practical applications. Beyond vaccine allocation, HeadStart can be used for randomized selection in medical resource allocation, price-linked savings, and fair lotteries. Its verifiability ensures public confidence in the randomness of these processes. After that, I want to give you a comparison about the HeadStart and also the existing work. As you can see from this slide, compared to existing protocols, HeadStart excels in scalability, verification efficiency, and RP latency. It just supports public participation and scale and ensures security with minimal computational overhead. And for the detailed understanding, we can refer to the comparison table on this slide. As you can see, we just attached the time complexity and also the three metrics and also every like other methods here. So we can have like a very clear comparison about the HeadStart and other algorithm or other existing works. Okay, so for the next, it is future work. Just looking ahead, we plan to explore just other groups of unknown order to achieve higher security with smaller parameters. We also aim to integrate HeadStart with real-world applications and also try to optimize implementation for even lower latency. And this is all of these just are future directions we can explore more. In conclusion, HeadStart just provides an efficient, scalable, and low latency randomness generation protocol. It just enables public participation with low computational burden, and it is also very practical for real-world applications, like what we have introduced before, like vaccine allocation and also fair lotteries, just these kind of things. Okay, so this is all about my presentation. Thank you for your attention. And this is also the end of our group's presentation. Okay, thank you very much. We're also very happy to take any questions you may have.